It is recording now. Should I just leave it on?
Sure. By the way, my Wi-Fi router has been crashing these past few days, so I'm a little worried that it might go wrong during this talk, but hopefully not. I don't have any other options, so.
It's okay. We'll just wait for you to join us again if it crashes. Willie, you have a very interesting background.
By the way, I'm very happy for people to leave their mics on or interrupt me a lot. I feel like it'll be nice to have some sort of like sense of an audience.
Oh, I think we both sent out reminders at the exact same time.
Yeah, I guess. Okay, so how about we start at like 5 after?
Yeah, I think that's a good idea. It looks like Shweta won't be able to join us.
Yeah, that's okay. I saw.
Yeah. I think it's very hard to find a time that's good for everyone.
Yeah. Oh no, how do I go back?
So is this content also in one of Mark's lectures?
Not entirely.
Okay. But it builds off of that? Or I'm just asking if there's some reading that...
Yeah, I mean, it's primarily from a single Unruh paper, but we'll just touch on stuff that's sort of all over the place too. So. Yeah, so 2 more minutes. People are still showing up.
Yep.
All right, thanks so much for coming. So this talk is about quantum secure commitments and collapsing hash functions. So I know there's slides and everything, but just to be clear, this is part of this Quantum for Dummies seminar. And this is more of an informal lecture about prior work, and most of it has nothing to do with the particular research that I'm involved in. So I'm giving this talk, but please don't treat me as an expert in this subject. And hopefully this can be a little bit more of a discussion than me talking at everyone else. Okay, so the focus of today is to talk about the right definitions for commitment schemes in the quantum setting, and sort of look at analogous questions for defining collision-resistant hash functions in the quantum setting. Okay, so just to start, I'm going to put up the definition of a non-interactive commitment in the classical setting. So we have Alice and Bob. Alice has some message bit M that she wants to commit to. So she samples some random string R, gets her commitment C, sends it over to Bob. And later on, when Alice wants to open this commitment, she just sends along her her message along with her opening R, and Bob just verifies that this actually equals C. Okay, so straightforward crypto 101 stuff. What we want from our non-interactive commitment is, for today, we'll say statistical hiding and computational binding. Okay, so we want that C statistically hides a message bit M, and that if Alice is efficient, then she can't adversarially change her mind after sending her commitment C. Okay, so this should be pretty straightforward. And for the rest of today, I'm just going to focus on this notion of computational binding. So I'm going to forget about the hiding entirely. You might actually notice that some of the commitment schemes we talk about don't even have hiding, but this can be addressed by working a bit harder. So feel free to stop me if that's an issue, but for the rest of today, we're going to focus on binding. Okay, so how should we define binding in, for a commitment scheme? Well, in the classical setting, this is pretty straightforward. We're trying to capture this notion of probabilistic polynomial time cheating sender can't change her mind after sending the commitment C. Okay, so classically we say, well, that means that she really should be stuck at a single message. So she shouldn't be able to open to two different messages, right? She shouldn't be able to find messages M and M prime that are different, as well as valid openings for them. Okay, so this is how we define it in the classical setting. And this definition exactly captures this notion that she shouldn't be able to change her mind. Okay. And in particular, any collision-resistant hash function gives you this property. Okay, so it doesn't actually give you a hiding scheme, but a CRHF immediately gives you a computationally binding scheme if you just use the hash function as the commitment itself. So you just apply the hash function to M concatenate R. Okay, so it turns out that this is not true for quantum attackers. In particular, if what you care about is this intuition that your quantum attacker shouldn't be able to change their mind after sending the commitment, this classical notion that you can't find two different openings doesn't actually seem to be the right definition. Okay. So this is the definition that we accept is the valid way to capture this intuition or this notion. But I claim that quantumly, this really isn't the right thing to go for. Okay, so in particular, there is a result by Unruh, building on a prior work of Binus, Rosmanis, and Unruh, that shows that there exists a quantum secure collision-resistant hash function, this H tilde, where a cheating quantum prover can open it to any M of her choice. So when you use this collision-resistant hash function as a commitment, Alice can send a commitment, and then after sending the commitment, she can pick any M she wants, and then open this commitment to that M. Okay, so if you think about it as a commitment scheme, that doesn't have, that's definitely not what we want, but somehow this is still quantum secure as a CRHF.
Question, yeah. What do you mean by a quantum secure CRHF here?
By quantum secure CRHF, I mean that a quantum attacker can't find collisions.
Okay.
So there exists a hash function where a quantum attacker can't find any collisions. So it can't find two different openings. Otherwise, it would violate collision resistance. But it still has this property that it can open a commitment to any M of its choice. Okay, so this is really highlighting the fact that this collision resistance notion is not actually the right way to define computational binding in the quantum setting.
And so how do they, so this is for the usual construction of commitments from CRHF? They say that a specific construction of commitments from CRHF is insecure.
Yes, yeah.
Okay.
Yeah. Okay, so I'm not really going to get into the details of this in particular because I don't know them, but I'll at least sort of sketch how this works, and so you can believe that it's plausible this could be the case. I should mention that this is actually relative to a quantum oracle, and we don't actually have a sort of standard model version of this result, of this separation. Okay, so here's what happens. What Alice, this adversarial committer, is going to do is it samples, it has some way of sampling some commitment string C. So this is a classical commitment along with a quantum state. And it has this property that after it sends the commitment, it can pick any M it wants, and then it can perturb the state accordingly, according to whatever M it wants. And it's going to measure the resulting state to get some R. And then when it sends along the M that it chose along with that R, the receiver will accept. And indeed, it will find some R's such that H tilde of MR is actually equal to the C that it sent. Okay. And the reason why this isn't ridiculous, this doesn't violate the collision resistance, is that the state is actually used up by this process. Okay, so this isn't something that that this adversary can do twice. So it can't actually find a collision because this is a one-time process. So you're going to measure the state, you're going to get your R, but then after that, there's no way of actually going back and trying with a different M. Okay, so this is sort of an important and subtle point here. So I want to pause here and take questions.
So I have a question.
Yeah.
So this still means that given a commitment string, a quantum adversary cannot open it to two different messages. You're just saying that the adversary can open it to some message, to an arbitrary message of its choice.
Yes, yes.
But it still cannot open it two different ways, because that would...
That is true, yes. But if you think about what you want from a binding commitment scheme, we really don't care if it can open it two different ways. We care that after it sent it, there was only one thing that it could have opened to. Right.
Okay. So for me, quick question. This is Vinod. You know, this new construction of Mark and others in stock this year, doesn't it give a concrete construction of these you know, commitments or hash functions without the oracle?
So I'm not familiar with that work, but I would be surprised because it would give quantum money.
That they do get quantum money, but you know, they think about it. One could think about it this as a feature, right? And that's, I think, what they do.
I see. Okay, yeah, I'm not familiar with the work. I should probably talk to Mark more.
Yeah. Okay.
Okay. Any other questions?
So yeah, to answer, I think the oracle that there still is an oracle, and they just basically heuristically instantiate it with obfuscation.
Okay. Good. Thanks, Dave.
Yeah. So the oracle in this Unruh example is a quantum oracle. In particular, it needs to do quantum things, and so we don't even have a candidate obfuscator for this.
I see. And Mark's thing is a classical oracle, so you can instantiate it. Got it. Okay. Sounds good.
Sure. Okay. All right. Okay, so I'm going to work towards motivating and defining the right way to think about computational binding for quantum adversaries. And so what we're going to do is we're going to break up our adversary into this sort of two-part adversary. The first part of the adversary, at the top, is going to come up with some commitment string C, and then she's going to output some state, some qubits representing her state, some qubits representing her messages, and some qubits representing the openings R. Okay, And it turns out that this is without loss of generality. So because we know that this the second attacker, the second phase of the attacker is at some point going to output messages, a message M along with a random string R, it turns out that you can trace back these registers and say that this comes without loss of generality from measuring corresponding qubits, these capital M and capital R registers. Okay, so we know that these capital M, capital R registers have to exist somewhere. And then I give this arbitrary state vector. So we know that there have to be some M and R somewhere, and then S just captures everything else that the adversary might want to write down. Okay, and S can be arbitrarily entangled with the M and R. But before I go on, I want to make sure that people are comfortable with the statement that I can frame an attacker this way, and this is without loss of generality, that there's a first stage attacker that generates a commitment C along with qubits SMR, and then the second stage attacker takes in this SMR and operates in this prescribed way where it's just going to measure the M and R registers. It's going to get these classical M and lowercase m, lowercase r, and it's going to send that as the message in opening. So far I haven't defined anything. I haven't worked towards actually defining what computational binding is. I'm just saying that any attacker in a commitment scheme is going to look this way. Any quantum attacker I can write down in this form. And breaking it up into this first phase and second phase attacker is going to make it a lot easier to write that definition down. So please ask questions if you're confused at this point. This is going to be pretty crucial for the rest of the talk. So I'll give this maybe 15 seconds. And
I think another clarifying question about the classical setting, I think, is when we look at statistically hiding commitments in the classical setting, we actually usually just only care about the fact that the adversary should not be able to open it two ways, not about the adversary not changing their mind once they're committed, because it's statistically hiding, so we don't even know what they committed to. I'm guessing that the reason that we want stronger properties in the quantum setting is because we cannot rewind and extract two openings and things like so. So maybe those types of commitments are useless.
Yeah, I don't have an immediate answer for you.
Okay, we can just discuss. I'll ask you later if I see.
It might come up later anyway.
Okay.
Vinod, are you saying something? I think your mic might be off.
Yeah. Can I ask something? So if you think about a 3-message protocol, like one of these usual 3-message protocols, I send a commitment and then I get a challenge back. If I can open to whatever I wanted, depending on the challenge, that's not so cool, right? So it seems like you need it. Maybe I'm missing something, Dakshita.
So I think in those 3-message protocols, again, how do we formalize that you need this? We rewind and say, well, we can extract two things.
Not an option here.
So I think that's what I was asking. Maybe, I don't know, maybe this is the same thing, but I'm just saying the concept of what the adversary committed to doesn't exist for these statistically hiding commitments, for example. So I don't know how to formalize what he committed to when changing their mind.
But I guess what I'm asking is, this constitutes an actual attack, right? For me, that's what you're saying. If the ability to actually do this, open to any value.
Mm-hmm.
After the fact, it does constitute. Does it constitute an attack against, some protocol?
I see. Generate a string.
I mean,
and open it. So if there's an efficient way to, right.
It should, right? I mean,
it's hard to imagine using a commitment in a setting where you're allowed to open it to whatever you want, and
right, like a 3-coloring protocol or something, right? I commit to a graph, and then I get and then I can open it to whatever I want. So where does the sound is completely breaks down, right?
But it can be useful in a deniable setting or something. The fact that you can do it, but you're saying as a commitment.
Yeah. So the fact that you can actually do this open to any message is actually terrible for 3-message protocols.
Okay, so I think in the classical setting, the two notions are equivalent. The fact that you open to any message, or you can open to two different.
Yes, yes, yes.
And they're not in the classical settings,
No.
I think.
Not in his, yeah, no, not in quantum. Yeah.
Sorry, not in the quantum.
Okay. All right, so if people are happy with this two-stage adversary, so the way that we're going to motivate this definition is to think about what a perfectly binding commitment looks like. And we're going to try to construct, or we're trying to give a definition that says we want to look computationally indistinguishable from a perfectly binding commitment. Okay. So when your usual definition falls apart, this is a good starting point. You say, look, what is the perfect thing, and how can I be computationally indistinguishable from this? Okay, so that's going to be the goal. Okay, and so what is, I guess, one way to capture the property of a perfectly binding commitment? Well, it says that if you give an opening, a valid opening MR for some commitment C, then this means that M had better be unique. Right? There's no qualifiers there. M just has to be the unique M such that there is some R that opens to this C, right? If it's perfectly binding. Okay, so we're just going to try to capture this definition. So here's how we're going to think about it. I'm going to describe a game, and this game is going to be the two sides of this game, the left and right hand sides of this game, are going to be perfectly indistinguishable for a perfectly binding commitment. And then our notion of computational binding for the quantum setting is going to be that these two sides are going to be computationally indistinguishable. Okay, so these games will be a little bit complicated, but bear with me. So again, we're thinking of these games as these two-stage attackers. So we're concerned with the ability of these two-stage attackers distinguishing from figuring out what side they're on. Okay, so in the first stage, right, this attacker comes up with some classical string C, and she outputs her qubits, the state S, her message M, and opening R. And what we're going to do as a challenger is we're going to compute this. We're going to compute this one bit, this Boolean value V sub C applied to M comma R. And this is just going to check whether or not the commitment, or sorry, the message and the randomness written in those registers are actually valid. Okay, so in superposition, we are checking if M and R are valid openings, a valid message opening pair for the commitment C, right? Because the adversary outputted C, this classical C, and that's going to define this this V sub C value, right? It's going to define whether or not this is it's going to define like what we're checking against, right? So we're computing this 0, 1 bit in superposition. And the next thing we're going to do is we're just going to measure this bit. Okay, so what we care about is seeing whether or not this actually is valid. So if we get a 1 from this measurement, that means that this state is going to collapse to a superposition over valid message opening pairs. Yeah, so if I get a 1, it's going to be valid pairs. And then conditioned on this measurement being a 1, we're going to do one further measurement. In particular, we're going to measure the M registers. Okay. And here's the thing. If it's a perfectly binding commitment, as we just discussed, this measurement does nothing. Right? So if it's a perfectly binding commitment, then the moment you see that this measurement, this V sub C measurement has turned to 1, we know that this this M register is uniquely defined. Okay, and when things are uniquely defined, they're not in superposition, then you can measure them for free. It's not going to disturb a state at all. Okay, so on the right-hand side here, I'm going to have the same thing, except I'm going to skip that measurement. This conditional measurement where if the verification passes, then I actually measure that M. I'm going to skip it on the right-hand side. But for a perfectly binding commitment, these two things are exactly the same. Okay, so, and our definition of computational binding is just that these two sides should be computationally indistinguishable. So another way to think about it is the left-hand side is kind of the behavior you get from a perfectly binding commitment. particular, on the left-hand side, the second stage adversary is going to get a state where M is already measured and therefore unique. Right? There's no leeway in the second stage's adversary. The second stage adversary's choice in M, right? Because it's measured. And on the right-hand side is what actually happens. Right, if the adversary is succeeding, then this is basically the state that it's going to get. Okay, so the right-hand side is what's actually going to happen when we give it the give it the real scheme, and the left-hand side is a perfect behavior, and we want to say that these two things are computationally indistinguishable. Right, so if these adversaries can't tell the difference, then they may as well have been working with a perfectly binding commitment scheme, and that's sort of the intuition here.
So formally, the indistinguishability is conditioned on the verification being, so the verification is 0, right? Both games abort, presumably.
They don't abort. They just we still pass it on. It's just the measurement doesn't happen.
Right. Okay. All right. Sounds good.
Yeah. Any other questions on this? This is maybe the core definition of the talk. Maybe the most technically complicated thing in this talk. Everything after this point is easier.
I have one question. So on the left-hand side, the fact that the final state is actually classical. So does that help you to go back to the original state?
Does that help you go back?
Like for instance, in rewinding, if you want to go back to the original state, you can do that.
Oh yeah. You're ahead of me. Yeah, exactly. We'll talk about that in a bit.
A quick clarification on what Vinod just asked. So we do need indistinguishability even if the verification outputs 0.
Yeah. That's baked into the definition of the game.
Okay.
Okay, so yeah, this definition is a little bit to unpack, but hopefully it makes sense. So really, you can go back and kind of derive this for yourself by just thinking about how does a perfectly binding commitment work, and then what does it mean to be computationally indistinguishable from this? Okay. All right, and Unruh shows that indeed these collapse binding commitments, these commitments meeting this new quantum definition of computational binding are called collapse binding, in particular because on one side you sort of collapse the superposition over the M's. So these collapse binding commitments are implied by things called collapsing hash functions. So sort of in the same way that a collision resistant hash function gives you your classical notion of binding, a thing called a collapsing hash function, which I haven't defined yet, gives you this notion of a collapse binding commitment. So in particular, if you just use the hash function itself as in sort of the canonical commitment, you get this collapse binding property. And if you want to go ahead and get some statistical hiding property, you can use the standard Halevi-Mikali trick where you commit to some universal hash of your message, and the binding property follows through. Okay, so this collapsing property, this is the collapsing property of a hash function, which I'm about to define, is in some sense the quantum analog of collision resistance. Okay, and we'll get into that in a little bit. But let me first define what a collapsing hash function is. So I'm just going to throw one more definition at you guys, but this definition is going to be a little bit easier than the last one. Okay. All right, so it's again an adversary trying to distinguish between two different worlds. And so they're going to do the same thing in both worlds up until the end. So what the adversary is going to do is it's going to come up with an arbitrary superposition over the input space. So capital H is our hash function, the X's are the inputs. It can come up with any superposition it wants over inputs. The challenger is going to evaluate the hash function in superposition. And depending on what the challenge bit is, the challenger is either going to measure the X registers, so the input, or it's going to measure the output. Okay. And we give this back to the adversary. So I wasn't writing it here, but you can also assume that there is some state registers that are, or some state qubits that are being passed from this first stage to the second stage adversary. And I think generally this isn't even written as a two-stage thing. It's just a little bit easier to think of when we just seen the collapse binding definition. But generally in the literature, this is the adversary submits something and then we just send it right back. So definitely some state is being passed along between these two-stage adversaries. Okay, so the point here is that a hash function is collapsing if no adversary can tell whether or not you measure the input registers or the output registers for any superposition of inputs of its choice. Okay, and these are indeed different measurements, right? As long as H is a compressing hash function, measuring the input is going to be different from measuring the output. Right, because if you measure the input, you're going to collapse to a single state, a single computational basis vector, this x comma h of x. And if you measure the output, you measure h of x, then you're going to collapse. So think about if the adversary submitted a uniform superposition over all inputs. It can do whatever it wants, but let's just say it did that. Then if you measure h of x, then this is going to collapse to all x. It's going to collapse to x comma h of x for all x that hash to that same value. Okay, so as long as this is compressing, these are two different games. Okay, any questions on this definition before I go on? Okay, so it turns out that if you construct a hash function satisfying this property, then using the standard classical techniques for building commitments from hash functions, you get the right notion of collapse binding of those commitments. And that is, it takes a little bit of effort to show this. And in particular, you need to show that this indistinguishability even holds for partial measurements, because for commitments, you're only measuring the M part of the input. So if you think about the canonical hash function, you're not measuring the whole thing. But it turns out that if you just work through some quantum, this is true. So
for me, the construction is again, you first universal hash your message, and then you no, the other way around, maybe you first apply a one-way permutation or something, and then you universal hash the. Is that right?
Yeah, I honestly don't remember off the top of my head, but it's
I see.
Yeah. I think if you sample some random X, you apply universal hash to it, you yeah, something like this. Yeah.
That's fine. Yeah.
But yeah, it's the Halevi-Macaulay construction, and it works as is if you start with a collapsing hash function. Okay. All right, so just for the rest of this talk, I'll touch on three things. So first off, talk about how collapsing is indeed a strengthening of collision resistance. So this is more of just a warm-up or sanity check. Then we'll look at how do we actually build collapsing hash functions, because these aren't very useful if we can't realize them. And at the very end, depending on time, if people have to go, I'll sketch applications to quantum rewinding, as some people have hinted. Okay, so let's see that collapsing actually implies collision resistance, that it's indeed a strengthening of the classical notion. Okay, so suppose you have an adversary that is actually breaking collision resistance. Then I want to construct an attacker that's going to break the collapsing game or win the collapsing game. Okay, so your attacker finds some x0, x1 such that there's a collision. What you're going to do is in the collapsing game, you're going to send the state psi, which is going to be the uniform superposition over x0 and x1. Okay. So the challenger is just going to evaluate H in superposition, right? It's going to get this state. And now it's either going to measure the input register. So if it measures the input register, what's the adversary going to get? Well, it's either going to get x0 or it's going to get x1, right? Or it's going to get this whole state, this uniform superposition over x0 and x1. Okay, and the point is that you can easily distinguish these, right? So if you look at sort of the space span by x0 and x1, there's in one case you're going to get the vector that lies exactly in the middle, or you're going to get one of x0 or x1. So you just do a measurement that is where the axes are aligned with this this uniform superposition of x0 and x1, and then you're going to be able to distinguish. You don't distinguish with perfect probability, but you need a non-negligible distinguishing advantage, so it's good enough.
So like for each bit, you do a Hadamard measurement, and then one of them is different, and then you're going to catch it with half probability.
Okay, so indeed, collapsing is at least as strong as collision resistance. Yeah, sorry.
So why would the challenger compute this? I think I'm missing. What is this game here? The adversary finds x0, x1, and then who sends?
Okay, right. So we're starting with an adversary that's breaking collision resistance, right? So we know it can find some x0 and x1, and we want to say that we can get an adversary that breaks the collapsing game. Okay, so what's the collapsing game? The collapsing game is the adversary can submit any superposition it wants over inputs to the hash function. So in particular, the superposition over these x0 and x1 that correspond to collision is allowed. What the challenger in the collapsing game does is it says, okay, you gave me that superposition. All I'm going to do is I'm going to evaluate H in superposition. And then depending on my challenge bit, I'm either going to measure the hash register or the output register or the input register. Right, so we saw that if you measured the input register, then you're just going to get either x0 or x1, and otherwise you're going to get the uniform superposition. And these two, just looking at it geometrically, they're distinguishable.
Thank you.
Any other questions? Okay. So now how do you actually construct collapsing hash functions? So in the first paper, this Unruh actually should be 16. Unruh 16 paper that defined this notion of collapse binding commitments and collapsing hash functions wasn't actually able to come up with a standard model construction of collapsing hash functions and left that as an open problem. But they did show through quite a bit of work that random oracles at least are collapsing. Okay, so there is like some hope that this is a reasonable, achievable notion. Okay, but then Unruh followed this up with another paper Asia Crypt 2016 that shows that if you have a lossy function with lossiness rate 1/2, you can use these to construct collapsing hash functions. And this construction is not terribly complicated, but a little bit more than I want to do for this talk. So here's another construction. So this is an observation with Ale, Nick, and Mark, that any somewhere statistically binding hash function, I'll define this if you haven't seen it, don't worry. Any somewhere statistically binding hash function is already a collapsing hash function. So these are actually introduced about the same time as collapsing hash functions. And it turns out that this notion, this purely classical definition, it actually achieves collapsing. Okay. And this is, I guess, this is unpublished, and you'll see why it's kind of obvious. One of those obvious in hindsight things. Okay. So I'll show this construction just because this is the easiest construction of collapsing that I know of. Okay, so what's a somewhere statistically binding hash function? So this is a hash function where I'm going to think of the input as being broken up into a number of different blocks. So just for simplicity, I'm only going to have 2 blocks, but in general, this can be many, many blocks. These are often thought of as the result of like some sort of Merkle tree built up over these blocks, where each block is a leaf of a Merkle tree. But here, I'm just going to think of 2 blocks. And so somewhere statistically binding hash functions have two properties. So one is their namesake, the somewhere statistically binding property, that says that, well, okay, you have this hash function that works in its normal mode, so that's denoted by this h. Okay, I'm conflating hash keys and functions. Hopefully that's not too confusing. But it has this normal mode h, but it also has these statistically binding modes. So we can generate a statistically binding mode of the hash function for any I we want. So I is indexing the different blocks. In this case, we only have 2 blocks, but in general, you can have it be binding to any block of the input. Okay, so if I give out this hi, then hi applied to x1 and x2 is going to be statistically binding to the ith block. Okay, so what does it mean to be statistically binding to the ith block? It means that the output contains, like statistically fixes the value of xi. Okay, so just to give you some more intuition for that, in the first construction of somewhere statistically binding hash functions proposed by Hubachek and Wicks, the result of this hash was actually an FHE encryption of the ith block. Okay, so as long as your FHE scheme has perfect correctness, then this is going to be like perfectly or statistically binding, right? If applying hi to x1, x2 actually gives me an FHE encryption of xi, then the hash function statistically contains all the information about xi. Right. And the second property we have is this index hiding property, which works really well in tandem with this somewhere statistically binding property. And the index hiding property says that the hash function in its normal mode h, the hash key is going to be computationally indistinguishable from the statistically binding hash keys. Okay, so I can switch the hash key over to be statistically binding on like the first block or the second block, or none of the blocks. And the adversary can't tell which block, if any, I'm being binding to. And intuitively, if you look at this, if you think about this FHE construction, if the result of my hash function is an FHE encryption of the ith block, you shouldn't be able to tell whether or not I'm actually encrypting something, or encrypting garbage, or encrypting which block. Okay, so this is a purely classical definition, but it turns out that any somewhere statistically binding hash function is collapsing. So here's how you see this. Well, so this is what we want to show, right? We want to show that these two hybrids are indistinguishable, or the top hybrid is just one mode of the collapsing game, and the bottom hybrid is the other mode. So the top one is the I measure the output mode of the game, and the bottom one is I measure the input. Right, so I want to show that these two are indistinguishable, and I'm going to use the somewhere statistically binding property to show this. Okay. So hopefully this is clear. I'm just I'm writing x1, x2 as the two different blocks of the hash function, but otherwise this is nothing we haven't seen before. Okay, so I'm starting in this first hybrid where we measure this. We measure the output of the hash function. And what we can do in this first step is, well, by index hiding, we can change the hash function to be binding on the first block. Okay. So that's immediate. And now we've switched to this h1, so hash function's binding on the first block, and that means that we can measure x1 for free. Right? Because we've measured h1 of x1 concatenate x2, then that means the x1 register is uniquely determined because this is statistically binding. This contains this that we've measured already fixed x1. Right? That's what statistically binding means. Okay, so that means I can measure the x1 register for free. So hybrid 1 and hybrid 2 are perfectly indistinguishable, or are statistically indistinguishable because of the statistical binding. Right, so I can measure this x1, and because it was fixed anyway, this measurement doesn't do anything. And that's basically the whole idea, right? So now I just switch the, I can switch h1 back to h, and then I can do this for every single block of the input, and And by doing this for every single block, I can then measure every single block of the input until I've measured the whole input. And so I just do the exact same steps for the second block, and then I can measure the input. So because somewhere statistically binding allows me to bind to every single block of the input, I can just step through all these hybrids and then gradually measure all of the input until I'm measuring the whole thing. And that's exactly what I want out of collapsing. And these somewhere statistically binding hash functions are implied by any lossy function. It's unclear to me if this improves in any way over the Unruh work. I think there is some like lossiness bound that he requires, and I'm not sure if that goes away here. But I think this is a maybe conceptually easier way of thinking about collapsing. So,
so Fermi,
yeah.
You know, somewhere statistically binding implies collision resistance, right?
So
in particular, the construction from lossy trapdoor functions would need lossiness rate at least a half. You know, it needs to be sufficiently lossy, it seems.
Yeah, you're right.
Then it seems like same assumption, but it's a cleaner proof, you know.
Yeah.
Sure.
Sure, you're right.
So I guess another question, is there a WOOF version of collapse binding? You know,
really good question. I don't know, but I was wondering this yesterday.
Okay, yeah.
This is something Justin pointed out to me, and I didn't get a resolution to this yet.
Okay.
Yeah. Any other questions? We're doing pretty good with time, so.
Yes, I have a question. So actually, is the assumption here that the adversary in these hybrids, he can only measure the state once and as we prescribe, or like, I don't understand why he couldn't measure, like mix up the measurements, I don't know, do some measurement on X2 and.
So the adversary, so when I'm saying measurement, I'm saying this is what the challenger is doing.
Okay, it's the challenger, okay.
Yeah, sorry, I've been a little bit unclear about who is doing what, but yeah, at the beginning, the challenger is measuring only the output register, and then gradually it's starting to measure more and more of the input register, and we're saying that at each step of the way, the challenger can get away with doing more measurements because of the statistically binding property.
Okay, thanks.
I guess this is the only part of the talk that isn't written down somewhere, but these slides are on my website. Okay. All right, and just to wrap up, I'm going to sketch some applications to quantum rewinding. Okay, so this is how we actually use these notions of collapsing to get some other crypto. Okay, so just going to briefly recall the notion of a sigma protocol, and not even fully recall it, just recall enough to be able to talk about what I want to talk about. So we'll be looking at sigma protocols for some relation R. In a sigma protocol, we have some prover, some verifier. They have some shared input X. The verifier is trying to learn whether or not X is in the language induced by the relation. The prover has an associated witness, and they engage in this 3-message protocol where the prover sends a message A, the verifier sends some uniformly random challenge C, chosen from some challenge space. The prover sends some response back, and just based on the transcript and X, the verifier decides whether or not to accept or reject. Okay. And these Sigma protocols will want to have a number of properties. I'm going to ignore all of them except for the special soundness property. Okay. Everything else is going to be irrelevant to our quantum rewinding discussion. Okay, so special soundness says that if you have 2 valid transcripts, so both starting with the same message A, but with 2 distinct challenges, C1 and C2, if the prover is actually given valid responses, so if the verifier accepts on transcript 1, which is A, C1, Z1, and also accepts on A, C2, Z2, then special soundness says that whenever you have this, you can actually efficiently extract the witness W. And special soundness is interesting because, well, what we actually care about is this proof of knowledge property, which says that if the prover is succeeding, then there exists some extractor that is actually able to output the witness. Okay. And classically, we know that special soundness implies proof of knowledge. Okay. And the idea is that if the prover is succeeding with some good probability, then it's going to succeed on 2 different Cs. So we just run it on one C, rewind it, run it on the other C, and then we take advantage of special soundness to get the witness. Okay, so classically, we know that special soundness implies proof of knowledge. And that's just through this rewinding. Okay, and as pointed out earlier, this does not hold for quantum. Right? And the problem is that measuring Z1 is going to disturb the state of the prover. And then once we measure Z1, we can't actually rewind and return to its original state and then try again with a fresh C2, Z2, or try with a fresh C2. And this is sort of the central problem about transporting proofs from the classical crypto world to the quantum one, is that you sort of have to resolve these quantum rewinding difficulties in a number of different ways, depending on your setting. Right. Ideally, what you'd want to do is somehow make 2 copies of the prover and then run them both. But we know by no cloning, we don't have some efficient unitary that will take a general quantum state and make 2 copies of it. Okay. So the resolution of this is, I guess, so simple that it's almost unsatisfying. But here it is. The idea is that as long as you have a sigma protocol that has some sort of collapsing property, I'm leaving this kind of unclear because partially because it's unclear to me, and partially because it's had a number of different definitions in literature. This was first this was first observed by, or this first constructed by Unruh, and then follow-up works that were more interested in the problem of applying fiat Shamir to these protocols in the quantum random oracle model, kind of abstracted Unruh's work. And so I wasn't quite sure which definition to go with, so I'm just going to say special soundness plus some notion of collapsing is sufficient to get, well, not a proof of knowledge, but an argument of knowledge, because this collapsing is a computational property.
So,
Yeah.
if you take a sort of a 3-coloring protocol, for example, right, instantiated with a statistically hiding commitment.
Yeah.
Why would you want to do that? I don't know, for fun. You know, not a statistically hiding commitment, rather a collapsing commitment, right? Can you rewind and extract now? Does that fall into this class?
I think if you set it up right, yeah. But I'm saying more about this in a second.
Can I ask a quick follow-up?
Yeah.
Do you need 2 transcripts, or can you generalize this to more than 2? The special soundness constraint says you can find W given these 2 transcripts that share the same first message. Does that generalize beyond 2? Because I think that with 3 coloring, you'd need more than 2 to find the right coloring.
Are you asking if we can get away with doing more rewindings?
Yeah, basically, yeah.
Right. I think the conjecture is that you can get away with some constant number of rewindings.
Okay.
You get some probability loss with each rewinding, and I think that at least I vaguely recall Mark conjecturing that it drops off like very quickly. But,
okay, I see. Okay, thank you.
Okay.
Yeah, okay, so I'm gonna briefly explain the main idea behind this, and I'm gonna sweep a lot of things under the rug. So if you catch them, I'll be happy to talk about them, but if you don't, I won't. Okay, so the way we'll think about this is, again, breaking the adversary into a two-stage adversary. So this first stage adversary is going to, it's going to send some message A, it's going to get the random challenge C, and then we're going to just pause the adversary at this point and look at the state of the adversary. And without loss of generality, the state is some superposition over these qubits representing S and Z registers, where S is just arbitrary state of the adversary, and Z is going to be the register that the adversary in the second stage measures to produce its response Z. Okay. And this measuring, right, so I'm thinking about this adversary. Without loss of generality, the second stage adversary just does a measurement, and then it gets this classical string and returns this. And doing this measurement is the step that causes rewinding to fail in general. Okay, because this measurement disturbs a state, right, how do we rewind the adversary? We're trying to, we want to rewind it and try it again on a different C. So we want to apply some kind of unitary to undo what the adversary just did. But once you do a measurement, that's not reversible. Okay, so yeah, I guess the resolution is so simple once you have collapsing, it almost feels like cheating. The point is that by collapsing, I can say that, and this is what I mean by some collapsing like property. It turns out if you design your Sigma protocol properly, so that the first message A is like the right sort of collapse binding commitment to something, you will get this indistinguishability, but in prior works, it's been generalized to be some property of the protocol itself. So this is more or less the property. It says that if, when the adversary passes these qubits, this state SZ to the second stage adversary, I could have paused this state in the middle and just performed a measurement on the Z. And by some collapsing property of the protocol, this two-stage adversary can't notice the difference. Okay. So this measurement, remember, is not actually happening in the real world, but we're saying hypothetically, if we were to introduce a measurement there, the adversary would not be able to detect it. Okay. So now let's switch to the world where we actually have performed the measurement in the middle. Well, now once we have performed a measurement in the middle, the second stage adversary who's going to measure that Z, well, nothing's going to happen because Z is already collapsed to be some fixed computational basis vector. Okay, so we introduce this measurement so that now when the adversary does the actual measurement, nothing's going to happen. Okay, so in particular, we are computationally indistinguishable from a world in which measurement is free. That's what collapsing tells us. And so you can get this, as I said, by designing the right protocol around a collapse binding commitment, or defining a collapsing sigma protocol, as I think it's explicitly done in Liu's Andry. I'm not sure if it's probably done in Don Fermi-Jensen and Schaffner too. You can define a protocol, a sigma protocol itself, to be collapsing if it has sort of has this property that you can do this switch. And I'm drastically oversimplifying things, but this is morally what's happening.
Hey, Fermi, can I ask a quick question?
Yeah.
So Unruh already showed that random oracles are collapse binding, and then it looks like these works require some additional work to get the Fiat-Shamir working, right? So what was missing?
Oh, probably not the right person to ask. I don't actually know how these papers work beyond what I Googled yesterday to make this slide.
Okay.
So I think you also need to generate the verifier's challenge C as the output of the random oracle and then prove soundness. And I don't think that that's what Unruh showed, right? Based on what you just said. Unruh showed that if you compute A using a random oracle, then that is collapse binding. Is that correct? Or?
I think so. Yeah, if anybody is more familiar with these works, feel free to speak up. But yeah, I'm sure it's something sort of like that. It was definitely like a big open question for a long time for how you actually apply Fiat-Shamir to, I guess, do the standard ID protocol to signature transformation in the quantum random oracle model, and that's what these works resolved. Okay, so this is basically what you do to allow the rewinding, because now you can do your measurement for free or computationally. It's indistinguishable from a world in which you can actually do the measurement. So you should just go ahead and do the measurement in the real world anyway, because the adversary can't tell the difference. Okay. So I'm lying a little bit because there is one detail that one fairly important detail I'm omitting, which is the fact that you also want to check that this transcript is actually accepting. And that is not something that we can use collapsing to say that like this particular measurement, checking whether or not ACZ is an accepting transcript, this actually like may disturb the adversary state. But it turns out that that we can handle this. This was actually handled in a prior work of Unruh 2012 that shows that you can handle binary, like random binary measurements. In particular, like you pick a random measurement that corresponds to the randomness of the challenge, and you perform a binary measurement just checking whether or not the transcript is valid. And if you perform a single binary measurement and it succeeds with, if you perform a random binary measurement and it succeeds with some probability epsilon, then performing that measurement twice in a row, where perhaps the first measurement disturbed the adversary state, will still succeed with probability at least epsilon cubed. So prior work of Unruh already showed that we can handle the fact that we're doing a binary measurement. Like that will disturb the state somewhat, but not too much. And that work, the Unruh 2012 work that showed this, didn't resolve this problem of measuring Z itself, and because that might disturb the state a lot. But once you have the notion of collapsing, you can put these two together. And using this, I think Unruh in the 2016 work gets quantum statistical zero knowledge arguments of knowledge for all of NP. Okay, sorry, I think there's a chat. Okay.
Can I ask another quick question?
Yeah.
What about, so where did we use the special soundness property?
Sorry, hold on, how do I go back? Okay. It's implicit. I guess I didn't show the second round, but I'm just saying that that this is just the first round, the first run of the adversary. I'm saying that we can actually do this run, we can actually do the measurement, and then we can now rewind and try with a different C. And the point was that because of collapsing, I'm allowed to do this in a way that doesn't disturb the adversary state in a way that it can notice. It does disturb the adversary state, but the point is that the adversary can't tell. So special soundness, like the only issue was that running this twice and measuring Z like the first time is potentially an issue. So I'm zeroing on the first execution and saying that this is actually okay now. Does that answer your question?
Yes, yes.
Okay. Okay, so yeah, it's been an hour, so let me just conclude with one open question. Also, I guess we alluded to this a little bit before. So we know that any collapsing hash function is collision resistant, but is the other direction true? And so the immediate answer is, well, of course not, right? We had a separation. But this counterexample is relative to a quantum oracle. So modulo some recent work of Mark that I'm not familiar with, we have this interesting question of, can we construct a standard model collision resistant hash function that is not collapsing? And it turns out that this would be really interesting. And this is Mark's paper that won Best Paper at EuroCrypt 2019. If you could construct such a thing, then this actually implies something called quantum lightning, which you can use to get a number of really cool applications like public key quantum money, certifiable randomness, which is it's sort of different than the notion that I guess recent works of Ermila and Zvika and others have considered. This is non-interactive. This is non-interactive, whereas I think theirs are interactive, and this certifiable randomness is publicly verifiable, although you need a quantum verifier. So this question of I guess separating CRHFs and collapsing is I think this ARU 14 and UNRU 16 paper, we're looking at this to try to answer this question of like which definitions are going to be sufficient to actually give me a commitment scheme. But it turns out that showing a separation actually allows you to build really cool crypto. And with that, I think I'm done. So thanks, everyone.
Thanks, Fermi. This was a fantastic talk. We'll likely have, we'll update you on email about when we have the next lecture in this series.
Hey,
If you want to volunteer, that would be great.
Yeah.
For me?
Yeah.
Can I ask a quick question?
Yeah.
No, so yeah, first of all, yeah, great talk. So yeah, I never thought of this random oracle recording queries as a version of collapsing property. So that was cool. Like the.
Oh, sorry. What do you mean by random oracle recording queries?
So in both these Fiat-Shamir works, essentially what they're saying is you can record the random oracle queries without the adversary noticing. Right?
Yeah.
And I guess what Dakshita was pointing out was that they also require programming of the random oracle.
Right.
Right. But if let's say you don't require programming of random oracle, then can you just use like a collapse binding hash function to instantiate it?
I'm not sure. I guess collapsing gets you like one particular property of random oracles, but you're asking if it gets you everything that is not captured by programming. I guess that if I'm understanding that correctly, that sounds unlikely.
Yeah.
Yeah, I think the whole recording quantum queries is right. That's a totally orthogonal front from collapsing, although it's not something I'm very familiar with.
Yeah, thanks.
I also have a question about these somewhere statistically binding hash functions.
Sure.
So you said that you can have any number of blocks, and my question is, like, how many blocks does it make sense to have? I don't know, because it looks like even if you have one block, it would work. So if you have more blocks, it's easier to get.
No. One block is the number, the only number that wouldn't work.
Okay.
If you wanted it to be compressing, then you can't have it actually be statistically binding to one block, because then it can't, like, then the output has to be longer than the input.
But then do we know like how? Because for example, I don't know, in the construction, in the example that you showed, you said that it could be an encryption of X and then an encryption of XI. This if you choose the index I.
Yeah, for any polynomial you want, I think for any polynomial number of blocks you want, you can construct an SSB hash function that takes in that many blocks.
But that doesn't pose a problem when you do the hybrid sequence. I don't know, isn't there like some kind of constraint there that?
No. As long as you have a polynomial number of blocks, you're only going to pick up some polynomial loss in these hybrids.
Okay, thanks.
All right. If there's no other questions, I'm going to stop recording at least.